Welcome to chapter 16. We will be talking about electrophilic addition or substitution. No, so EAS. EAS, yes, electrophilic addition substitution. That is the mechanism that we'll be predominantly talking about, and this is for aromatic compounds. Now, aromatic compounds were introduced to you in the previous chapter. You said this is an aromatic compound. And they react a certain way. They are a functional group of their own. And what about the nomenclature here? So hopefully you realize that this portion of the compound is an aniline. So that's aniline. And so this would be, the relation here is 1,4, which is para bromo aniline. So para-bromo-aniline is D. What is the classification of this compound? So whenever you see the heteroatoms, you need to put in your lone pairs. And then you ask, is this cyclic? Yes. Is it planar? Yes. Is it fully conjugated? So is everything sp2? Yes. Then you do your pi electrons. And so if it's 4n plus 2, it's aromatic. If it's 4n, it's going to be anti-aromatic. And so we count 1, 2, 3, 4, 5, 6. So 6 pi electrons. You count a lone pair, one lone pair, when you do not have a double bond to the heteroatom. So we've talked about that. When to count that lone pair as one of the pi electrons or when to not. So this would be aromatic because 6 pi electrons fall into the 4n plus 2. Okay, so welcome to chapter 16. Electrophilic aromatic substitution. I call this EAS. And basically a hydrogen is going to get replaced by an electrophile. And so the key is to have strong enough electrophiles. So what I want to see is when you have a set of reagents, I want to see the electrophile. So whenever you get a set of reagents, I want to see the electrophile. And then, so I want to see the electrophile for your reaction mechanism on these. And then I want to see your sigma complex, which we'll talk about that. That's an intermediate, that you can name that. And then I want to see your aromatic product. So these are the three things that I need to see. And then, of course, I need to see your curved arrows for your reaction mechanism. So benzene does not undergo addition reactions. Now, they do not undergo electrophilic addition like what we saw with bromine or HBr. Okay, so benzene doesn't do that like other unsaturated compounds. Okay, the substitution of hydrogen keeps the aromatic ring. The reason for the EAS, you want to reform the aromatic ring. It's very hard to break up the stabilization of the delocalized electrons of the aromatic ring. So we call this re-aromatization. So it's going to re-aromatize, and it does that, and that's why you get EAS. It's a thermodynamic sinkhole. These are the different reactions that you're going to be required. And so you see that if you add a Lewis acid like iron 3 chloride with chlorine, then you can get a reaction. Now, what I want to see here is that you just write Cl plus. If you have bromine with iron 3 bromide, I want you, for your reaction mechanism, to show your electrophile, because this activates the Lewis acid, and you'll see the slides of how electron donating and back donating to generate the electrophile. This is nitric acid with sulfuric acid, and this electrophile is the nitrogen plus. Okay, you see the electrophile? So I want to be able to, that's part of the mechanism. When you have fuming sulfuric acid, which is sulfur trioxide added to hydrogen peroxide, you get SO3 and the plus on the sulfur, so that's your electrophile. These are Friedel-Crafts acylation and Friedel-Crafts alkylation. Alkylation and acylation, you'll see that's an R plus. That's a carbocation. You'll see that. I need to see the carbocation. When you get the carbocation, you have to have the most stable carbocation. Anytime you get a carbocation, you got to look for the rearrangements. And then here, this is the acyl cation. And so what's being added to the ring, you'll see, is wherever the element that gets the plus charge. So in this case, it's the nitrogen. In this case, it's the sulfur that's going to make the sulfur-carbon bond. This case, it's going to be the carbon. And in this case, it's going to be the carbon. So I need to see where the positive charge is on these molecules. Okay, these electrophiles, because that's where you're going to get your new bond for your substitution. And the hydrogen on the aromatic ring gets replaced. By this electrophile. So what's the mechanism look like? So your electrophile, and this is where I want to see the double bond. You can pick whichever one you want. You need to draw in your hydrogen. And so if this is like Cl plus, this is a slow step. And that means on the energy diagram with reaction progress, this is going to be a very high activation energy. So if you remember, the height of that tells you the speed of the reaction. So here, this valley here will be your sigma complex. And so here's your sigma complex. So once you get a new bond formed with your electrophile, so in this case, your electrophile could be Cl, then you get a positive charge on this other carbon. This is the sigma complex. This is your intermediate. And they're showing you all the different resonance stabilized carbocations. And then what happens is you're going to have something like, this is a before. This is going to act as your base then, because it's a catalyst, and deprotonate this. This step is what we call re-aromatization. And that re-aromatizes the ring, and that is going to be an exothermic process. So they're just showing you that these resonance structures stabilize this sigma complex. This is the reaction energy diagram. There's your sigma complex. The rate determining step is the first step when you add your electrophile to the aromatic ring here to make your sigma complex. And then this next step is the re-aromatization. and that's always taking a hydrogen away and reestablishing the single, double bonds in the ring structure. So this is going to go over all the different reactions. We have halogenation reaction, and halogenation reaction, benzene is going to react with either the Cl plus or the Br plus, and that's going to make a aryl halide, which is a chlorobenzene or a bromobenzene. And these are fluorine reacts too violently. Iodide is too slow. So basically the only halogenation reactions you have is the chlorination or the bromination. And you're going to see what I expect when you have these reagents is you just show your electrophile. I expect that. And then I expect to be able to see you drawing your hydrogen here for both of these, because this is the bond that you choose to form your sigma complex. I expect to see your sigma complex. So you put the chlorine there, and then you put your carbocation there. There's your sigma complex. You don't have to draw your resonance structures at this point, but you should be able to. And then we do the rearomatization, which in this case you could just do FeCl4 minus, goes and abstracts this hydrogen that's bonded to the chlorine, and then those electrons are going to go to reestablish the aromatic ring. Same thing here. If you want to see your hydrogens drawn in at the two carbons, your sigma complex, you got a new bond to the bromine. The other carbon gets a positive charge, and then in this case, you get re-aromatization. That's what you're seeing here. This is a Lewis acid, means the Lewis acids will accept a lone pair. And so this Lewis acid will accept a lone pair from the bromine to make this complex. This releases a very positive electrophile, and it's that electrophile that's been activated that can now be reacted to overcome the high activation energy to give you your sigma complex. And then you have the reactorization. You can see that here we deprotonate that, and the rearomatization gives you your product. Chlorination proceeds in a similar mechanism. This is just showing you some biologically active alkyl chlorides. Well, Butrin is an antidepressant, so this was chlorinated here. Antihistamine, that was a chlorination. What's interesting is about a third of your synthetic drug molecules or synthetic compounds have a halogen in them. And in nature, it's very rare to have a halogen in a molecule. But synthetically, over a third, you get halogenation. This is Agent Orange, which is very bad herbicide that remains still in the soil today. Nitration and sulfonation. So this is when you have nitric acid and sulfuric acid. This is going to be your electrophile that I want to be able to see. And then what happens is you draw in your hydrogens here, and you draw in your, you're going to make your sigma complex. So here you have the hydrogen, you have your nitro, actually that's nitro, and then you also have this hydrogen here, and then basically HSO4 minus will come in and do the rearomatization to give you aniline. Sulfonation, these sulfur trioxide and sulfuric acid make this electrophile. And then you can draw in your hydrogens. You can show the sigma complex here. You don't have to draw a second arrow because sulfur has d orbitals, which is expanded octet. You pick one of those carbons. At this point, it doesn't matter. And then HSO4 minus will come and make sure you get your positive charge there. Do the rearomatization to make a benzene sulfonic acid. So this is showing you how to generate your nitro electrophile. Basically, sulfuric acid has a lower pKa than nitric acid, which means it's more acidic, and so it's going to deliver the proton in the presence of the nitric acid. These are very both strong acids. And then you're going to lose water as your leaving group to generate your electrophile. I just expect you to be able to draw a Lewis structure of your electrophile. And then this is showing you how to generate the SO3 hydrogen. Sulfur trioxide gets protonated in the presence of the strong acid. And then this is going to make the SO3 plus electrophile. What is the missing reagent in the following reaction? Okay, so we're doing nitration. So what reagents give you the nitro electrophile? Nitric acid and sulfuric acid, B. What is the major organic product in the reaction below? All right, now this is not one of those reagents, but it is a reaction you do know. If you have a tertiary alcohol, and you know alcohols are horrible leaving groups, but you have it in acid. So you get protonation of the alcohol. This was organic 1. Okay, so now you have a great leaving group, and a tertiary alcohol will just leave. And when that leaves, it gives you a positive carbocation. And so now we got this tertiary carbocation, so it's not going to rearrange, and that's a strong electrophile because you have a positive charge. So let's draw our sigma complex. Here. And then we can draw, this is that carbon. You see? So you got to make sure that the new bond is between this tertiary carbocation and the ring. And now we have, you just have water, which would rearomatize. And so that would be D. So Friedel-Crafts alkylation, and alkylation means you're making carbon-carbon bonds. Alkylation, we're going to alkylate it. So when you add a Lewis acid to an alkyl chloride, then that Lewis acid will create the carbocation by helping the Cl be a great leaving group. So something like this would give you this carbocation. And you have to look for carbocation rearrangements. As you see here, a tertiary carbocation does not rearrange. You get your sigma complex, just like you did in all the other E's reaction mechanisms. Here, This is the bond that you want to pay attention to. And then you have the 3 carbons here. 1, 2, 3. And then you're going to get reatomization, which will be the aluminum trichloride. It's going to be like aluminum 4 chloride, and it will rearomatize to give you the product. Aluminum chloride is also a Lewis acid, and so Lewis acids accept a lone pair. If you look at the structure of aluminum, you would see that it has these unhybridized p orbitals, and so then the chlorine will take its lone pairs and donate them to aluminum trichloride, and then that gives it an R+. And that's what you're seeing here. You form this electrophilic complex that helps pull the Cl away, and that gives it the carbocation. This carbocation then reacts with the aromatic compound to give a sigma complex, and then the sigma complex will re-aromatize to the aromatic product. So vinyl halides are unreactive because they're sp2 carbon chlorides. Aryl halides are also unreactive, sp2 carbon chlorides. So you're looking at sp3 carbon with chloride. The other thing, you have to have a Lewis acid, and this generates your electrophile. Here you have a secondary carbocation, so you need to check with its neighbors. If you switch places here, that would be a primary, but if you switch places here, it would be a tertiary. Tertiaries are more stable, so you will expect a hydride shift. And then when you do that, you need to draw your new electrophile, and it's that electrophile that's going to react to form the sigma complex. So when that happens, you can draw your sigma complex and make sure that you get the right structure here. And then that gets a positive charge. And then the aluminum 4 chloride will do the rearomatization. So you can see that you had rearrangement. Same thing here, the primary. If you have that carbocation, it will rearrange to form something like this, the secondary, through a hydride shift. And so that is the actual compound you're going to make. This is showing you that rearrangement. It's when you generate your electrophile, the carbocation. Then you get a secondary carbocation, so you get a 1,2 hydride shift to get a tertiary carbocation. It is this carbocation that will react with the aromatic compound to generate your sigma complex, and then rearomatization for your product. Rearrangements can often occur even when there's no free carbocation. So even with a primary, you can get this, because it's like a complex, you can get this happening, like an internal shift here, and that will happen. Other functional groups that form carbocations can also be used as starting materials. So it doesn't have to just be the Friedels-Crafts alkylation with the Lewis acids. You know that an alkene with sulfuric acid, this electrophilic addition, you protonate the alkene to give you remember the Markovnikov? Okay, so you get the carbocation, and then that could react with an aromatic compound such as that. So to get your sigma complex, So this is a hydrogen there. That's a positive. This is a hydrogen, but then you get this new addition here between this carbon and that carbon. And then you get reatomization. Okay, here you got a tertiary alcohol and sulfuric acid. You saw that in the previous slide to give you a carbocation. So Friedel-Crafts acylation, this is when you have a carbonyl. So we have a carbon, this is called a carbonyl. So you have an acid chloride. The carbonyl bonded to Cl, that's an acid chloride. That might be a new functional group for you, acid chlorides. And when you add that with the Lewis acid, aluminum chloride will take away the chlorine to give you this electrophile. And it is that electrophile that then gets added to the aromatic ring. And now you get a new acyl group. What's nice about this is you don't have rearrangements because this is not a carbocation, so there's no rearrangement. This is showing you how to generate your electrophile. You can do the psyllium ion. Notice that carbon has 4 bonds. This puts the positive charge on the oxygen. You don't have to do that for me. I kind of like having the positive on the carbon because that's the new bond you're going to make in your electrophilic aromatic substitution reaction. And so here, you have to come up with the reagents that would make this compound. If you try to do something like this, what would your electrophile be? Well, see, this gets protonated, right? It gets protonated and then you lose sulfuric acid to give you this carbocation, which is a primary. And so the problem is this would rearrange to a secondary, could even rearrange to a tertiary. So that's not going to work because this is a primary. Same thing here. But these are reagents you need to know. So A is the answer. The first one here is this structure, which is an acid chloride, an aluminum trichloride, aluminum 3 chloride. This is going to give you the aselenium cation. Sorry, that's a cation. So the sigma complex will add there. Then you re-aromatize, so you'll get this compound here. And then the nice thing about this is called the Clemmensen reduction. You need to know these reagents because mercury and zinc with HCl will remove, if you do this in HCl, will remove that carbonyl. And it's reduction. The hydrogen's coming in from HCl and it will replace the carbon double bond to just hydrogens. And this way you can add Friedel-Crafts acylation followed by reduction to get you your product without rearrangement. There's not another way in these reagents to do this. This is an example of an intramolecular acylation. I've actually done something like this at Lilly. It's really a sweet reaction. So this will generate your electrophile. So there's your electrophile. And then what happens here is you have your hydrogen there. Now you have this intramolecular reaction. And you'll see that that's 1, 2, 3, 4, 5, 6-membered ring. So keep everything else the same. You have your hydrogen here. This is going to be a plus. This is a hydrogen here. And then you have your carbonyl on this carbon. Okay, so that's the carbonyl. And then you have AlCl4 minus due this hydrogen that gets subtracted to form, reestablish that aromatic, the rearomatization. And this is called an alpha tetralone. It's a ketone. Ketone. You get a new carbon-carbon bond to form a ring. This is the fused ring. Intramolecular reactions for 5- and 6-membered rings, this is a 6-membered ring, are faster than intermolecular. Intermolecular reactions are when you have two things that add together. This is an example of an intramolecular Friedel-Crafts acylation to form this tetralone, this alpha tetralone, in the synthesis of LSD. Many substituted benzene rings undergo electrophilic aromatic substitution. So this is when you have substituted benzenes. So what's nice about all those reactions is your starting material is always benzene. If you notice, that was always your starting material. Well, now we have substituted benzene. So now it makes a difference of what carbon-carbon double bond you get. So here, when you have benzene, it doesn't matter if you pick this double bond or this double bond or this double bond. You just get to pick. But when you get a substituted benzene, it matters. Okay, so we're going to start looking at reactions where your starting material might be toluene. Or what if it's aniline? What if it's phenol? What if it's a nitro group? Okay, so these are examples of substituted, or what if it's a benzoic or some kind of, benzoic acid or something like this. So you see how you have different substitutions. This is substituted benzene, and now it's going to matter if you pick this double bond or this double bond. Are you going to pick this double bond or this double bond? You can pick this double bond or this double bond. And I will show you, you'll have to kind of memorize or make a chart and classify the substituent. Is it electron withdrawing group or is it an electron donating group? And you'll find that if it's an electron withdrawing group, then you'll want to pick one carbon over the other versus electron donating group. So what determines whether something is electron withdrawing group or electron donating group and where the substituent, the electrophile, is going to add which carbon depends on several factors. One is inductive effect. So this is in the sigma bond, and so nitrogen is more electronegative than carbon, so this has somewhat of an inductive effect. Carbon versus carbon, it's going to be pushing the inductive effect towards the carbon. So is it donating, electron donating, or is electron withdrawing? There's also resonance effects to consider. So, but I'm just going to go straight into the most important one to consider. If the element that is bonded directly of the substituent bonded to the carbon has a lone pair, then that's going to be electron donating. That's going to trump everything, okay, because that's going to show you some resonance. That is the most dominant factor. So here, this donates those electrons, and then you can see that those electrons are delocalized through all of these different resonance structures. If you have a carbonyl will be an electron withdrawing group. So here, the electrons in this resonance structure go up here to give you a positive charge on that carbon. So now you have a positive charge on that carbon, which pulls those electrons, and instead of donating electrons in the ring, it makes every carbon around the ring a positive. So the most important thing is going to be pretty much your resonance effects for directing. We call these directing groups. So you're going to find that electron donating groups, if they donate electrons into the ring, they're going to be orthopara-directors. Orthopara-directors. And we'll talk about that. And you're also going to find that electron donating groups are they increase the reactivity rate of reaction. So that's electron donating groups. Electron withdrawing groups will be pulling electrons density out of the ring, and their directing is meta. They are meta directors, and they slow the reaction down. And so electron withdrawing groups would be anything that gives a positive charge. So we just saw that a carbonyl through the resonance structures become a positive. Okay, so then that gives a positive carbon. Nitro is probably one of the number one electron withdrawing groups because nitrogen's always positive. And so this determines whether, if you have electron donating, so if you have a lone pair, it's going to be electron donating group, and that electron donating groups will increase the rate of reaction. And what are we comparing it to? Increase the rate of reaction compared to benzene. And so benzene does not have a substituent. So if you have halogens are weird because they're both electron withdrawing groups, but they have lone pairs. And so what you're going to find out is that they're slower than benzene, but because they have a lone pair, they are orthopara-directors. And this is kind of just showing you the electron maps, density maps. So electrophilic aromatic substitution is a general reaction of aromatic compounds, and you consider two things: the rate of the reaction. So a substituted benzene can react faster or slower than benzene itself. So we've talked about that. The orientation, these are called directing groups. So they're either going to be ortho-para directing groups, or you're going to get a meta directing groups. And so those are the two things to consider. So here we have toluene. So we have this methyl group, and that is an electron donating group. So it's going to be faster than benzene. So the reaction is going to happen faster than benzene. And it's going to be an orthopara-director. So when you draw your sigma complex, well, you go ahead and make the bromine electrophile. And this is your ortho group. So we can show the sigma complex where the bromine adds ortho. So now we do have to care about which hydrogen we put the carbon on. So you can see that this bromine is 1,2 to the methyl group. So that's ortho. So that is okay. This is your sigma complex. And then iron bromide will deprotonate this hydrogen to do the reatomization. Ortho is 40%. If you need to do your para, and you only have to show one, para is 60%. So I'm okay with ortho or para. You can show one or the other. You can show both. But also note that you don't have any meta. trace is considered 0. Okay, so what about the nitro group? Well, if you draw the Lewis structure out, and that's kind of how you're expected to problem solve in organic chemistry. So here we have the Lewis structure of the nitro. That's what the nitro is, right? NO2 plus, your electrophile. Well, you got a nitro, but then this is also a nitration. So here we do this. We take this electrons to do the sigma complex. Hydrogen, hydrogen. Now I have to decide which carbon am I going to put this on. Am I going to put it on the ortho or am I going to put it on the meta? This is a positive. See the positive? So this is electron withdrawing group. It's going to be slow and it's going to be a meta director. So now I'm going to pick the meta. And then I'm going to put my positives there. And then for re-energization, I will show that mechanism. Do you see 93%? That nitro is going to go 1, 3, meta. It's going to be your major organic product. All right, so here you have to decide, you have a substituted benzene. This is a delta positive. All right, so that's going to be an electron withdrawing group, and that's going to be a meta director. So this is the nitration, is your electrophile, and here you have the ortho positions, here you have the meta positions, and here you have para position. So it's going to be, this is ortho, and it's not the right reagents, right? What gives you SO3? SO3 and H2SO4. This is going to add a nitro. So even though this is meta, it's not the right reagents. Here this is meta, and this is para. So C is your answer because this carbonyl is electron withdrawing. So here you have substituents that activate a benzene ring. When they activate, and they're also ortho para director, and notice what do they have in common? They have lone pairs on the element that's directly bonded to the ring. So any of your phenol, these would be like aniline. These would be an ether. This is a reversed amide, so that's an amide, but notice the nitrogen is the one that's bonded to the ring, and R is just a methyl group or any kind of alkyl group, and those are electron donating groups. And when they say they increase the activation, that means these are going to be fastest compared to benzene. This is still faster than benzene, but notice that phenols are going to react faster than toluene. Here, this is the meta directors, and you notice like CHO is an aldehyde, which if you drew the resonance structure, you would see that that is a positive charge on the carbon. So we can even say that's a delta positive. Same thing here. That is a ketone. This is an ester, carboxylic acid. Nitrile, if you drew out the structure of nitrile, you would see that you did the resonance structure here. It would give the carbon a positive, or just two. So that gives the carbon positive. So nitrile would be a positive carbon, positive sulfur, positive nitrogen. and this is a positive nitrogen. Also notice that these are increasing deactivation, so these are going to be slower than, say, an aldehyde. Now, the weirdos are the halogens. They're ortho-pair director, but they deactivate the benzene ring, means they're going to be slower than benzene. So they're going to be slower than benzene itself to react, but they are going to direct ortho-para. And so we're going to spend the next few slides showing you why these different substituents, like electron donating groups, are ortho-para directors, and why electron withdrawing groups are meta directors. So we're going to show you why. And so we have to look at the mechanism, and we have to draw the sigma complex, and then we draw the resonance structures of the sigma complex. You have a good POGL exercise that shows this. So this is the rate determining step, the first step to get our sigma complex. Okay, so and if you have electron donating, you can see the different transition. They're showing you that the transition state for electron donating is going to be lower in the height. So this is going to be smaller than benzene. So benzene is going to be higher. And then electron withdrawing groups are going to be the highest. And so it's the height of this first mountain, this first uh, curve that you have to overcome that determines the rate of the reaction. So now talking about ortho-pair directors versus meta-directors and why. So you draw your sigma complex, and then to explain why, you evaluate the stability of the intermediate sigma complex. So here, if you have toluene, which you know is an ortho-para director, so these are the preferred products. Well, let's look at their sigma complexes, and let's look at the resonance structures of these sigma complexes. And so here is a secondary allylic, here is a secondary allylic, here is a tertiary allylic, tertiary, see? And then here, we should do our sigma complex, that's secondary allylic. Here is a tertiary allylic and a secondary allylic. And we know that tertiary carbocations are more stable than secondary. So this is why the reaction is faster, because there is a stable intermediate. If you try to make it go meta, the only thing is this is secondary, this is secondary, this is secondary. There's just no tertiary. It's not that it's bad, it's just this is going to cause the reaction to be faster to the point where the meta doesn't happen on a toluene, an electron donating group. What about an amine? Amine, you have the double bond here. Double bond, you have a lone pair that once you draw your sigma complex, you have a secondary allylic, but then this one is even better than the tertiary allylic because the lone pair can then make this more bonds. So this is your major, because you got more bonds, this is your major contributor. Remember we rate an organic one resonance contributors, and you look at the factors? Well, this is a factor that you can get in ortho and also in para. The only thing is, in meta, you just don't get it. You never get that because you never get the positive charge on this carbon for your sigma complex. And that's why it has, it's very fast. Nitro, okay, so the nitro, you got to consider that nitro is if you draw out the Lewis structure, it puts a positive on the nitrogen, which is an electron withdrawing group. And when you do your sigma complex, it is a meta. That's the preferred product, and it's no big deal. It's just, it gets a secondary carbocation. But what's This is a bad thing, though. This is a bad thing. You see how you got a positive next to a positive? That's going to repel each other. Here we got another positive next to a positive. It is so destabilizing that this isn't happening. And that is why you get the meta. And it's a slow reaction. This is a nice slide that just shows you overall that these are going to be activating. They're going to go faster than benzene. They all have kind of a lone pair. They're electron donating groups. And they're also going to be ortho pair directors. Notice that the halogens, even though they're not activating, so they're going to be slower than benzene, but they all are ortho pair directors. These are slightly positive carbons, sulfur, nitrogen. These are going to be slower than benzene because they're deactivating groups, and they're also going to be meta-directors. So the substituent that gets added on to make a disubstituted benzene product is going to be on the meta. So let's just look at some examples here. You have a phenol. A phenol has its lone pairs here, and we know that's electron donating groups, and we know that's an ortho pair director. So they're showing you it's so activating that it's even hard just to get one bromine that adds. But you don't have to worry about that. You can just show me either, I'm okay with the major product being this one, as long as it's ortho, or you can say para. Okay, so I know that you know that that's an ortho pair director. Here, this is just showing you that. Okay, what about this one here? It's a strong deactivator. You won't even get a reaction here because it's so slow, and Friel's craft is slow. I don't care if you give me a reaction, I'm going to count it right. And so what I would want to see is that this is going to go meta. So I'm okay if you give me a product, but it does need to be meta. Here, this is, once you activate this, sometimes you can get polyalkylation. Once again, I don't worry about that, but if you had something like benzene, I'd want to see, or toluene, that you got an ortho pair director. So they're just showing you, okay, so what if you have two donating effects? What if you have, so you're going to make a tri-substituted product. Well, you got nitro that is a meta director, and then you have toluene, the methyl, that's an ortho director. It can't go para because you got nitro in the para. Which one wins? The activating one wins. So this one's activating, so it's going to happen fast. So the ortho is going to win. So, and remember, you got to write that for your electrophile. Here we have, once again, you just, what's the activating here? You draw in your lone pairs, and you see that the ortho is going to be stronger activating. It has a lone pair, so you can look that that is going to be more activating than a toluene group because it's faster reacting. Here we have two methyls, and so this one would do ortho. That would be ortho. That would be ortho. That would be para. That would be para. So these aren't going to happen because this would be meta to this compound here. So these are, that's para. So it's ortho to one, para to the other, ortho, para. So you just either, this is meta director, this is ortho. Ortho's going to win because it's going to be faster. So you're going to get either here. Here, they're showing you multi-synthesis, so you do your bromination. And now this is going to be an ortho pair director. You're going to put the nitro is your electrophile here. So you can have either ortho or para. There's your para, and I'm okay with you showing one or the other. Here you got benzene, you do the nitration reaction. So you add the nitro, and now you need to know that that's a meta director. So then the bromine is going to add either here or there. All right, so which set of reagents would produce this product in the highest yield? What if you have two of these? Which ones do you add first? Well, what if you had the bromo? So let's do retrosynthesis. So what if you had this compound here? Well, bromo would add where? It is a halogen, so it's an ortho-para director, so it could add para. And what would that, and then, so that would do that. What if you had the other one? Okay, so here, this is electron withdrawing group, and it's going to add meta. So then if you did that one, then it would add meta. We see how are these related orthopara. So you're going to have to start with the orthopara director. And then you go, so the first reaction is going to be, you instill that first. So you start with benzene. Okay, and the first thing you want to do is put the bromine group. And since that's orthopara, because these are orthopara, you want to do an orthopara director first, and then you can do these. So what's the requirement here? Bromine and iron, well, aluminum bromide, Lewis acid, some form of Lewis acid, that gives you the bromine. And then this is Friedel-Crafts acylation. So you want an acid chloride, and then you need a Lewis acid as well for the Lewis chloride, Lewis acid. So the first thing you need to do is the number 1, and then the second thing you need to do is the Friedel-Crafts. So B is your answer. Okay, so I want you to kind of just to go over the nucleophilic aromatic substitution. You might get a question on this. I don't teach this much, and you will get only maybe 1 question to 10 questions for ease, but I just want to, so the nucleophilic aromatic substitution, NAS, I call it NAS, and I think of this as nasty, okay? Ease, I think, oh, that's easy, okay? So ease is, we do like maybe 10 of these reactions to 1 of the NAS, which is kind of nasty. The reason why it's nasty is it's a slow, they're meta directors, they're slow reactions, meta directors. This is harsh conditions. It doesn't want to happen. And this means like the nucleophilic compound, the nucleophile, is going to just do a substitution, and it's not SN2, okay? There's 2 mechanisms, and you don't have to spend a lot of time on this because, like I said, this is like a 10 to 1 kind of question. But there could be addition, elimination, or elimination. And so they're showing you how do you get NAS to occur. The nucleophile has to add, and then that's addition. And then you have to get an elimination. You see how this is eliminating? So you have addition, the nucleophile adds, and then you have to have elimination. The key here is compounds that are going to undergo NAS have to have lots of nitro groups. Okay, so this has 2 nitro. They're very electron withdrawing groups. So they're going to be slow, and fluorine, it's amazing fluorine's even a leaving group, but the halogens are the ones that are going to get replaced with your nucleophile. So here you have very electron withdrawing groups. So the types of compounds that will even undergo, benzene will not undergo NAS. You have to have some electron withdrawing groups. Nitro is typically, you also notice you got it at 300 degrees, 170 atmosphere. Okay, this reaction is even a waste of your time to even look at it, because guess what? You can biphenol. And the time you take a very uh, a molecule that you're working really hard, you're not going to want to add it to sodium hydroxide, 300 degrees at 170 atmosphere, um, because that is harsh conditions. But in the textbook, they show you this mechanism where you can do elimination and then addition, but you're not going to do it. The key here is to know that you're going to have a harsh nucleophile, and like I said, you just, I don't know. I wouldn't spend a lot of time on this because you're not going to get much of this. And it's just going to confuse you when you have to understand SN2, SN1, E's. Um, I will just put it out there so you can look at it, but like I said, I wouldn't spend a lot of time on that. Now this is another of aromatic compounds. This is kind of important though, benzylic. So this is free radical. We've done free radical reactions where you abstract a hydrogen to get a radical. And so these are halogenations of alkyl benzenes. These are reaction conditions where that would be the hydrogen that gets abstracted. In these, you have initiation, you have propagation, and termination steps. So you might want to review those. And so that's just showing you the initiation step. The propagation 1 step is an abstraction of this hydrogen. It has the lowest bond dissociation energy. And then you propagate in P2 another bromine radical. And that's how you can do benzylic bromination. We've seen allylic bromination. This is showing you ionic versus radical. So if you have iron with iron 3 bromide, this is ionic, see, because you get a very strong electrophile. You got to think about this being electron donating group, which is going to be an orthopair director. Keep in mind, if you get bromine and free radicals, there's your bromine initiation. And now you've got to think about bond dissociation energies and be like, oh, there's my hydrogen that I'm going to abstract. This is going to be my propagation product. And then we get radical conditions. So be on the lookout for those. That's important. And it shows, be on the lookout for competing reaction reagents. Also, oxidation of alkyl benzene. So this is a very important reaction. Potassium permanganate, as long as you have a hydrogen on that benzylic position, it will oxidize to a carboxylic acid. Notice that there's no hydrogen on this tertiary carbon, so you get no reaction. Look at here, we have secondary methylenes here, and you get phthalic acid. And this is a very common reaction scheme to do. You can also, we talked about the Clemmensen reduction, which is mercury, zinc and mercury and HCl, and that will remove the CO2. So these are acidic conditions. This is a decarbonylation reaction. So you actually remove the carbonyl group. And the other one is a Wolff-Kishner. This is going to be basic. I have done this reaction in the lab. It uses rocket fuel, which is hydrazine. This is hydrazine. You have to be careful with hydrazine because, like I said, it is rocket fuel. It's some pretty nasty stuff. You use sodium hydroxide and heat, but it's a basic way, if you have acidic sensitive compounds, that you can put this and see sodium hydroxide versus HCl, and that's another reaction reagents that will reduce the carbonyl, reduces replacing carbon-oxygen bonds with carbon-hydrogen bonds. So bringing all this stuff together, synthesis of alkyl benzene. You start with benzene. You can do Friedels-Crafts acylation, and then you can do reduction. And that is a way to make alkyl benzenes, and that is the preferred. So they're showing you here, this is a primary alkyl halide. So when you do your electrophile, you see that that's a primary that's going to rearrange to a secondary, and that's why you get this reagent and this is not formed. So one way to do that is to do the Friedels-Crafts acylation. This is acylation. And now you make a new bond here. And so you don't have to worry about rearrangement. And then you can do the Clemmensen reduction to remove the carbonyl to get your propylbenzene. Nitro groups can be reduced as well. These are some of the conditions. This is kind of like the Clemmensen reaction. HCl is your hydrogen source and an iron. I would not use tin. Tin gets on the brain and will not, and it'll cause insanity. I've known people that have had worked with tin and they lost their mind. So don't work with tin if you can avoid it. You can also do hydrogenation here. And iron and HCl is okay as well. But these nitro groups can get reduced to the aniline. And that's something that is a way to make benzocaine, which is a local anesthetic. So here is an example of if you have benzene, you can methylate that, right? Friedels-Crafts, methyl chloride with iron chloride. That would give you the toluene. And then that's a orthoparadirector, so we can get this with nitric acid and sulfuric acid. Now you have the nitro group. And then how do you oxidize that? Remember, potassium permanganate can make the nitrobenzoic acid. So multi-step synthesis here, you got to, that's what we just talked about. What reagents would you do and what steps, order of addition, 1, 2, and 3. And you have to specify that. Otherwise, it's assumed that you've added everything. There you go. So that wraps up this chapter.